Hello everyone, welcome to ashatech.com. Today we meet to discuss another important concept in mechanical engineering science called the Poisson's ratio. Now consider a rectangular bar as shown below, subjected to a tensile load P. Under the action of this load, we have to observe that the bar will increase in length by an amount sigma L, giving a longitudinal strain in the bar of epsilon L, which is now the ratio of sigma L, or the change in length of the bar divided by the original length. Now, when you observe this bar, which has been subjected to tensile load P, there is going to be an increase in length along, of course, this axis, but there will be an amount of reduction of the breadth and depth. Therefore, the width or breadth is going to reduce by an amount. From this side it is going to be del B out of 2, the other side also be del B out of 2. So generally it will reduce by an amount del B, and then depth will reduce by an amount, a corresponding amount of del D. So we have said the bar will exhibit a reduction in its dimensions laterally. Its breadth and depth will both reduce. The associated lateral strains will both be equal, but will be of opposite sense to the longitudinal strain, and will be given by, if this is lateral strain given by this symbol, it will equal to del B. If we take breadth, it will be negative del B divided by B. It will also equal to negative del D divided by D. Now, provided that the load on the material is retained within the elastic range, the ratio of the lateral strain and longitudinal strains will always be a constant. And this constant is what we are referring to as Poisson's ratio. So Poisson's ratio, therefore, given as V, is equal to the ratio of lateral strain to longitudinal strain. And therefore, this we have already said, longitudinal strain is equal to change in L divided by L. We know lateral strain, and therefore we can give the Poisson's ratio. Poisson's ratio V will equal to lateral strain, which is lateral divided by epsilon longitudinal, and this will equal to, if I take a breadth, the lateral strain along the width or the breadth, it will be negative del B divided by B. Then I divide it by the longitudinal strain, which is del L, or the small change in longitudinal, the small change in length divided by the original length. But we know from Young's modulus E equal to longitudinal stress divided by longitudinal strain this means del or sigma, which is used to mean stress, divided by the longitudinal strain epsilon L it means therefore I can say this Young's modulus E is equal to this sigma divided by longitudinal strain. Now if I call this one equation star, I already know from here, I know Poisson's ratio given by longitudinal, given by lateral strain divided by longitudinal strain. It means if I call that one equation 1, then I can compare equation 1 and star. We have said that 1 is like V, which is the Poisson's ratio, is equal to E lateral divided by E longitudinal. So I can eliminate longitudinal strain here for me to get the expression of lateral given Poisson's ratio and Young's modulus and the stress. Therefore, from equation star, we can see that longitudinal strain is equal to the stress divided by modulus of elasticity, and therefore it means again from equation 1, the lateral strain will therefore equal to V times the longitudinal strain, which is given by sigma out of E. Therefore, lateral strain will therefore equal to Poisson's ratio times stress divided by modulus of elasticity of a material. Thank you so much for watching. Follow us in our next lecture.